before I came back to India.
Okay.
I hope you're enjoying it as much as me. I love the Irish music and dancing and
Right, right.
singing,
It's
and
very
they
good.
have a
Yes.
fantastic, culture, and very
Yes,
friendly people
that's
is
true.
what I found them to be.
That's true. That's true.
So, Debasis, of course, people here are not here to hear us chat about Ireland. They're here to listen to your research work. And, I've been kind of introducing to them a little bit about the fact that you've been working in information retrieval. And I love the topic. It's very close to my heart, the societal implications of deep
Right.
learning and machine learning in general.
Right.
Do you want to check if you can share your screen and all is well there?
Yes, let me do that.
Wonderful. Yes, I can see your screen.
Let me go back to the start. Yeah.
Brilliant.
Okay.
So
Can
I'll
you see my
hand over to
screen?
you. Yes,
Okay.
yes, we can.
Okay.
Thank you.
Okay. So thanks a lot for giving me the opportunity to talk. So thanks a lot for the invite by Sarabjit and by Partho as well. So he was the first who invited me. And it's been a great pleasure for me to prepare the slides and then talk in front of you people. And so I'm going to talk briefly about a journey towards explainable AI, because I think this is a very important topic nowadays. Since the inception of the 2016 paper, which is called LIME, or Learning Interpretable Models for Explanation, this research community has worked a lot on trying to figure out why do we need explainable models for AI. So I'm going to talk briefly about the motivation for explainability in AI in general. And then I'm going to briefly present how what is the mechanism behind the explanation models. So this is not going to be very technical, but I'm trying to present examples, and then I'll try to make things clearer from examples point of view. There will be briefly there will be some equations which I'll try to explain as well, but it won't be that much of technical content. Then I'll talk about how potentially could we use. So when I talk about explanations, it's mainly about classification models and regression models. That's what the initial work was based on. But researchers nowadays, they are trying to apply explanations for other fields as like recommendations, like information retrieval systems, where you will feel the same need of explaining your predictions as well. So I'm going to talk briefly about some of my own work in that field, like how does explanations work specifically for information retrieval scenarios. And then I'm going to talk about some of my own thoughts about how we could apply explainability in conjunction with existing concepts in machine learning, specifically active learning. Because in active learning, you start with a situation where you have a small subset of the data, and you need to build on the data set gradually, because you need to select a subset of data and show them to annotators so that you'll get labels for the samples that you are throwing at them. So carefully choosing this subset of samples that we eventually show to the annotators could be helpful in building classifiers, so that they are not just effective in terms of classification accuracy, but they could also be helpful to build systems that are easier to explain. Or in other words, they'll be able to, or we might be able to build systems that we can understand better. And if we can understand better, then we could control the systems in a better way. So that's the whole motivation behind using active learning to build up easy to explain models. And this possibly has some societal benefits as well, because you could especially in today's field, where there are lots of talks about building ethical AI models. Like we had this situation a few months back in US about this Black Lives Matter, that you don't want to make any predictions that are, that are making some generalized statements against, some specific race or some specific gender. So human history has had a long history, of these cognitive biases that existed throughout these years. But we are gradually getting over these biases. And if AI systems again pick up these biases from the data, so that is something that's not fair. So in able to build or to develop ethical and fair systems, we should be able to understand the systems better, and then understanding them better will give us more flexibility in controlling them as well. So this is something that I'm also going to talk about. So without much further delay, let's start. So what we want to do is, like, I'm sure that you have seen Rick and Morty, maybe. So Rick is, he's a very technical person, and then, he's a scientist. So he always explains things, in technical jargons, and then he uses, very, very technically, very, very complex words to explain something, which his grandson, Morty, unfortunately is not able to understand. So even so, in terms of AI, so what we would like to do is, we don't want explanations like Rick's. So we want simple explanations like Morty's. So your model could be doing very complex things like Rick does. So as a scientist, he can do plenty of complex things. But Morty, from a point of view of a 12-year-old boy, he won't be able to understand, what Rick is saying. So Rick should be explaining his working principle or a working mechanism in simple terms. So say, for example, if Morty asks, which movie should I watch? So let's imagine that you build, a text classifier system that takes as input movie reviews. And the objective of the system is to predict, given the movie reviews, how good is the movie? So, if Rick comes up with an answer that, okay, so I've got stack layers of feed-forward neural networks over convolutions of, word embeddings. So this is lots of technical jargon, right? So it's difficult for somebody who is not from the deep learning field to understand, what the hell is Rick talking about? So like that's the question that we all have. So from Morty's perspective, if you are building a classifier, or if you're building an AI system, and then you're deploying that, so people, let's say, you're deploying something for the medical domain, right? Then doctors won't be understanding this jargon. So you should be able to say, how is the model working in simple terms, maybe in terms of the vocabulary that they would understand. So this is the thing that we want to solve. Yeah. So why do we need to give explanations? So one of the reasons is that in the recent years, let's say in the last 8 or 10 years, there is a huge paradigm shift from feature-based learnings to data-based learning, so which is popularly called deep learning in the literature. So previously, what used to happen, humans used to design the sets of features that were useful to build up classifiers, because so we humans used to build up the abstraction from the data. So data used to exist as vectors of features that we humans were, constructing. So that involved the feature engineering step. So let's say, for example, you want to classify, whether, given an image of an animal, let's say a cat or a dog, you'd want to classify, whether that's the cat or a dog. So maybe 20 years back, people used to extract features like, whether the animal has got whiskers or not. So if it has got whiskers, then probably it's a cat. Something like that, right? So then humans used to have their own way of thinking, right? So the way we perceive the world, we used to build the abstract features from the data. But nowadays, so that has its own problems. I mean, that will give rise to explainable models, because you completely understand how the model works. Because you just say, if you got whiskers, then you know that is an important feature, and if that's not present, then probably the model is going to decide that it's a cat and not a dog. But for the data-driven models, all you provide as inputs to the models is the whole data. So it's the whole image that you feed in as an input to your classifier. So in that case, we don't have any clue about, how is the model, coming to its decision. So we know what it does. We know it involves a two-dimensional convolution, and it tries to abstract out, some of the features that we would have done probably. So if you do so, you can look into, or we so that's what we try to do, right? So we try to draw a correlation. So like, what are the abstract features that the model is learning, which is obviously, dictated by the class labels that you are feeding in. So you're feeding in images of both cats and dogs, and you are telling the model that these are cats and these are dogs. But how is the model building up the abstraction internally? So that's something that we will want to look at. And then we want to feel comfortable that, whatever abstraction that the model is doing, it kind of correlates with what we would expect. So that's something. So if that happens, then we'll say that, okay, so this is an acceptable, explanation that comes from the model side of things. So we could say that, okay, so if the model has figured out that it should concentrate on the whiskers part of the animal image, if it's present for cats, then we understand that how does the model work. So it correlates well with our own way of classifying, whether something is a cat or a dog. So that's something that we would eventually, hope to achieve, right? So a good explanation model from a human side of things is like, if you throw in the raw data instances, and you know that in deep learning models, it builds up some abstraction of the data given your labels, does that correlate well with human perception? So if that happens, then we know that, it's a good enough explanation. And then it's easy to explain as well, because, to somebody not from your domain, you could just say that, okay, so I've built up a classifier, and this is the feature that the model is putting more emphasis on. And then you know that everybody will believe or everybody will trust your application or your classifier system. So that's how, AI systems, need to explain themselves to humans. Like, I have an example here, like, how do you convince, for example, like, if you think about convincing a medical practitioner, I have an example later on. So maybe, so let's say that you have a medical record, and then, you'd want to classify, what is the disease that the person is likely to have. And, if you are just saying that, he has a flu or not, maybe the doctor is not prepared to believe, why, he can ask a question like, why does the system come up with this prediction? So showing him, so for text, for images, we could show, regions of the images that corresponds to higher weights. We can have some, we can have some gray label pixel intensity, which could be, lighter for higher weights and then darker for lower weights. So we could impose that, heat map image on the top of the real image to visualize what's happening. For text, what we could do is we could come up with, histograms of weights, where we could say that, okay, so these are the terms, which has got higher weights. So, if he's looking at a document about a case history of a patient, if you could highlight terms like, I don't know, cold and sneeze and probably fatigued, then the doctor could kind of believe that, okay, if the system is predicting flu, then it makes sense because it correlates well with his perception. So there are two aspects to explanations in AI systems. So the first is trusting, or first is explaining a particular instance. So if you are predicting, given a collection of images about cats and dogs, given a particular image, if the system is predicting that it's that of a cat, then all you need to do is to provide an explanation only for that instance. So this is per instance based explanations. Typically, that is something that's done. So all the explanation models, they would take as input, one particular instance of the data, and it would try to find out weights of the different pixels. If it's an image, it will try to find out weights for different pixels. And then, by looking at it, a human could kind of see that, okay, so as I would have done, this is how the model is working. It's putting more weights. on this part of the image than the other ones. So these are, per instance, explanations. And another explanation is like at the aggregate level of the whole model. So it's not just looking at individual instances, but you could look into, you could ask like, how is the model performing overall for all the classes, for all the instances? Like, if I have in place a classifier about animals, cats, dogs, I don't know, whales, apes. So is it able to, classify them into their proper classes? So in that case, what you need to do is you need to sample, you know, quite a lot of instances from your data, and then kind of convince people by saying that, okay, so then you need to move on from per instance aggregations, per instance expansions, to aggregate them somehow, into an overall picture for the model. So in that case, what we'll do is, so we look into the per instance feature weights, and then try to select instances, which kind of cover this whole set of features in a broad sense of the term, or in an overall sense of the term. So let's say, for cats and dogs, so it's not just the whiskers for cats, but the other features for dogs as well, and other features for apes as well. So if you can highlight, all those features, by choosing a sample set of images and then say that, okay, so these are the ones, for this class, for cats, this is important, for dogs, these are important, and for apes, these are important. So if you can show all of them by selecting this subset of instances and looking at their feature weights, so that will serve as, an explanation for the whole model. Yeah, so as I talked about, so you have got two levels of explanations, the prediction level and the model level. So in prediction level, we explain the predictions of any classifier or a regression model by approximating it locally with an interpretable model. So I'll come back to that, with more examples and pictures. But this is what happens, right? So you have an instance, and then what you need to do is, you might have a very complex function or a complex decision boundary. So you have to choose that particular instance and then select points from the neighborhood of that point, and then try to figure out a very simple way of explaining how is the classifier working in that local neighborhood. And for the model level, we have to we have to choose a set of representative instances to explain the overall principle of the model. So here are a few examples. So in this example, you could see that we have some complex model, which we don't really have an idea about how it works. It takes in some documents about some medical reports from patients, where you have so these are like whole sentences or natural language sentences about the patient, and then let's say we have a classifier which predicts if or what kind of disease does that medical record indicate. So in that case, if I say that this person has got a flu, I need to explain why. So if I can highlight, or if the classifier can highlight terms like sneeze and headache and no fatigue, so probably it's not a flu because you don't have the fatigue, but you have the positive symptoms of sneeze and headache. So at least so the system would know that there is some conflicting evidences here. So from the system's point of view, also it could say that, okay, so I'm not feeling that confident about this classification for this particular instance. So it could be shown to a human for review, and then he could know that, okay, so where is the model getting confused? So the model is getting confused that it has got two positive evidences and one negative evidence, and then the human can override this output from the classifier, and then he could say that, okay, so I believe that it's a flu or not flu. So he could take on from that point. But if the system is not aware of itself, so if it doesn't know, or that, okay, so why am I classifying this document to the flu class? Then it can't come up with it can't come up with the confidence values, and it can't possibly tell to a human that, okay, so I'm not feeling that confident about this decision itself. Okay, so I have another example here. So in this case, you could see two documents. So there are two classifiers here, algorithm 1, algorithm 2. And the objective here is to classify a document. So these are emails. So this is called the 20 news group data set. So you need to classify it to one of the classes. So I think one of the classes is atheism and other is science or something. So in this case, it's classified to the class atheism. But then the classifier one, puts higher emphasis on the term God. So it classifies it to atheism, which probably makes sense, because when you talk about theism and theistic beliefs, you hope to find the word God, and you hope that whatever classifier or whatever decision the classifier is taking, it's based on those words. But for the second classifier, it looks at some arbitrarily common terms which has got nothing to do with atheism at all. It looks into terms like posting and host and reply and HTTP, and then somehow magically it says that, okay, so it belongs to the class atheism. We are not really sure what's happening here, right? So there is something wrong that goes to the classifier. And although it's classifying this instance to be in its proper class, or to be in its true class, but we as humans, we won't be trusting this model, because it's deciding its output based on some other, based on some irrelevant sources of input. So this is also, so if you see the explanation weights, you could kind of see that, which model, so you could choose across models, right? So you could choose that algorithm one is more trustable than algorithm two, although you see that both of them achieve fair enough or close enough accuracy values, you would want to deploy algorithm one and not algorithm two. So this is, this could be helping to decide that which one should go into the production environment. So it could be, like which could be more trustable, given not just a sample data set of benchmarks, but over a long period of time, we can put more trust on algorithm one than algorithm two. So this could be useful, for deploying AI systems as well. And this is another image. So, so just like in text, you can highlight some specific terms and say that, okay, what's the weight of these terms and the presence or absence of terms. Similarly, for images, you could, for every pixel in the image, you could try to estimate the weight of that pixel, and then you could gray out some of the pixels for which the weight values are below a threshold. In this case, we'd want to classify the type of this image. So let's say we want to find out if there is a guitar in the image or not. So it turns out that if there is a classifier like this, and if it outputs its decision based on this part of the image, so we could feel more comfortable with the classifier, because it's trustable, because it has been able to find out that part of the image which corresponds to a guitar, and it puts more emphasis on those words and on those pixels, and then that's on the basis of these pixels it comes to a decision. So in that case, we can put more. So we know that it correlates well with our way of thinking, and then we can put more trust to this classifier. Okay, so after the introduction, I think we can go to somewhat technical details about how an explanation mechanism work in general. So the first thing is that it should be interpretable. So as I was talking about for images and text, that for text it should be weights of words that you could show. For images it could be regions of images you could show. So every pixel would have got a weight value. So it should be locally fiddle. So it should have some kind of local fidelity as well, because we should look at how the model behaves in the very close vicinity and not overall. So your data set, your data space could be huge, but maybe in the explanations they don't really work well for that whole data set, right? Because it could be very diverse. Your set of inputs could be very diverse. So all we care about is like when we want to explain an instance, we want to look at other similar instances and then see how it behaves for those similar instances, right? So I don't know. So just to give an example, if there are if two instances are very similar, but the class labels are different. So say, for example, in the earlier example of the flu, let's say you have got sneeze, but you don't have headache and you have fatigue. So in that case, probably it's a different disease. I don't know what disease would that be. But let's say that document is very close to this one. And then, so maybe that's a different disease. And if the system is able to say that, okay, so for that disease, I come up with this explanation, and for this one I come up with this explanation, then probably that would be sufficient, right? So we don't need to look at the whole space of all medical records. So that will be like hugely different from this instance. We just want to make sure that, okay, so if the features are very close, or if the documents are very close, or if the images are very close, then how would the AI system behave differently? That's what we're more interested in. So the model has to be, has to have some sort of local fidelity. And the explanation mechanism itself should be model agnostic, right? So we shouldn't make any assumptions about the model itself. Like, so it could have, I don't know, for a text classification, you could have LSTMs, or you could have one-dimensional convolutional networks, or you could have even autoencoders, which learn compressed representations of a document, and then you could have a feed-forward network on top of that. So we don't really care about how does the model behave, or what is the the exact working principle of the model, or what is the exact mechanism of the model. We just want to know that given this input, we get this output. So what are the features that the model is considering, right? So that's what when we have this automated explanation method, from its perspective, how does the model work internally? That should not matter, because if that would have mattered, then we'd have to come up with different expansion algorithms for different models that came up, right? So that's not possible. So from the point of view of the explainer, the internal working principle of the model is not important. So this is something that should not, and it should not affect the decision of the explainer itself, right? So the explainer should just look into the inputs and outputs. That's it. So from the explainer's point of view, the model is a black box. Okay. So I think what we need to do. So we talked about the per instance based explanations. Where we talked about that. For every instance, we aim to learn the feature weights. So we could think that the feature weights also form a vector space. So we could think that given an instance X, we'd want to transform that to another space, that comprising of the feature vectors. So you can say that for every point, you transform that to an explanation space. So the way we do that, so I'll talk about that in the next slide. The way we do that, we sample instances from around the point that we want to explain. And that's how we learn the local view of the model. So this example will make things clearer a bit. Let's imagine that you have this point that you want to explain. So this red cross over here. So let's say you want to explain this point. So what you do is you sample other points from the data set that are very close to this one. So if this is an image of a cat, you'll get other cat images which look very similar. Like if this is a white cat, you will get other white cats, which are probably here. And let's say, the classifier is about classifying cats from kittens. And let's say this will be, so this is a different class, right? So then these will be white kittens. So maybe kittens don't have long whiskers. Maybe they don't have any whiskers. And cats, they will have whiskers, right? So the thing is, we're looking into, for explaining, this particular cat image, we're looking into other kittens and other cats that are similar with respect to other features. They are white, or they are, I don't know, maybe they're put in a basket, or things like that, right? So they should be looking very similar. And then you'll have some other instances which are not that similar, right? So this one, so this size over here, it indicates the similarity of the current instance with the other ones that you select, right? So this one over here, it's a bit small compared to these ones, because in terms of the feature space, it's not that similar to red. It's quite distant apart, right? It's quite far apart from this one. So probably these won't matter for us, right? So generally speaking, we could include them, but then we could include them with smaller weights. So that's what we do, right? So we sample and then we kind of use the similarity of the present instance with the rest of the other instances to learn a function, a simple function. So the simple function that we learn, so this is a very complex function, right? So it has all this zigzag way of classifying instances. We don't want to explain that. I mean, it's not possible to explain it, for all the instances, because that will involve complex decision boundaries. You could have white cats, you could have black cats, black kittens. So let's focus on one particular instance for the time being. So in this case, the red one. So then you could say, okay, so in this vicinity or in this close neighborhood, of white cats, in particular setting, these are the ones that are similar images. And then for that, we know that this is, or these are the sets of features which the model puts more emphasis on, right? And these feature weights are obtained by learning a simple, a linear classifier, and the parameters of the classifier, you could attach or you could associate to that particular instance, right? So whatever linear parameter you learn, this it will have some parameter values, which you can imagine as a feature vector or as a set of vectors or a vector with some values, and that you can consider to be the representative of that particular instance. So this is what we do, right? So we start with some let's say this is the raw pixel, the x. We transform that to phi x. So phi x is this line over here, and then we say that okay, so this x is transformed into some exponential space. It could be the same space of pixels. So for images, you could transform it back to the same set of parameters. So if you have like 100 cross 100 image, you could say that I have got 100 cross 100 parameters. So then you get an image, right? So where you know that every every point in this or every number in this transformed space corresponds to some pixel in the original space. And then you could overlay the two images. And then that's what we did for the other example here, right? So when we showed this example of the dog playing a guitar, so we transformed it back to the space of the image. Let's say it's 100 cross 100 pixels. And then you could know that these are the weights, these are the pixels which has got higher weights, and we grade the other ones out. And then you could know that, okay, so this image is transformed. So if this is x, this is phi x. You transform it to an exponential space, and that serves as your expansion vector for this particular instance. So this is just generalizing that and then expressing it a bit formally. So the objective function is so it looks a bit daunting, but it's not. So theta is the given classifier, the complex one. Let's say stacked autoencoders, stacked LSTMs, for text classification, or some very complex multi-layered two-dimensional convolution layers for image classification. So if theta is a complex model and x is the particular instance that you want to explain, so what you do is you sample points from the neighborhood of x. So that's why the summation is here. So z belongs to neighborhood of x. So neighborhood of x, it's very easy to get because you can sample random bit vectors, and you can take the component-wise product of these two vectors. So u is a vector comprised of zeros and ones, and then if you multiply it component-wise with x, so you'll get another instance, where you will have some bits that are matching with x and some that are grayed out, right? So this could be, because if you gray out very small, regions of the image, you get another similar image, right? Or there is another different way. So you could actually look into the data instances, the true data instances, and then select the ones that are quite similar to x. That's also possible. So there are two ways of doing it. So either you could form pseudo instances or you could form real instances. So you could take real instances from the data itself. But whatever way you do, you have some neighborhood, and in this neighborhood, you need to get the labels of that point. Like, talking about this figure, if you take the neighborhood region, then you know that, okay, so this point is also red, this point is also red, but this one is a blue one, this one is a blue one, right? So you know their labels as well. So this is that. So this is the this is the predicted label for those points. So we are not dealing with the true labels here. So we are dealing with the predicted labels. So I'll talk about that in another example. So these are not true labels. These are predicted labels. So here the model is predicting that this particular instance belongs to the red class. The model is predicting that this particular instance is belonging to the blue class. So you look into the predicted labels, the predictions that come from the theta model, the complex model, and then you have the simple model, the linear model, phi. So you want to approximate phi, you want to approximate theta, with the phi parameters, right? So you learn a simple square laws, right? So, you have your inputs, the z's in your neighborhood, so which is the phi dot z, it's a linear transformation on those points. And these are the predicted labels here will act as something like, if you're training a linear regression, then these would have acted as your true y values, but these are not true y values in this case. These are the predicted y values that comes from theta. And these are the predicted values that come from your simple model. So in that case, if you minimize the square loss, then you're trying to approximate how theta works, with a very small set of parameters phi on a very small set of instances, right? So that's what we learn in the objective function. So we're trying to approximate theta for a subset and with simple parameters, with simple linear parameters. Okay. This is the algorithm. I don't think we need to go into the details. So one thing that you should keep in mind that, we are taking some kind of a kernel function, right? So the way, we have drawn that figure, the kernel function ensures that, you put more weights on the points that are closer to the current instance that you were explaining. And for the other ones, so it could be Gaussian kernel, right? So as you move further away, then the weights decrease, and then it would, any data point that is further away from the current instance, would have less contribution to explaining the current instance. That's what you do in the kernel function. Okay. Yeah, and this is one important point, as I said, that the labels that we are using to learn the behavior of the complex model are not the true labels, but they are the predicted labels from theta, right? So the expressions will change. If you look into, so if you have an instance, and then let's say, it's a multi-class classification problem. So typically we'll have a softmax at the output layer. And let's say there are 3 classes, and let's say the probabilities are very close to like 0.33 or 1/3. So the classifier is not really sure about, whether, it's a cat or a dog or something else. Then in that case, believing, so you could take, or you could try to explain. So for this current instance, you could try to explain that, if there are 3 classes here. So electric guitar and acoustic guitar and Labrador, right? So if it's a dog, or, what's the guitar type that it's playing. So in that case, you could say, or you could say that, okay, so if I want to extract regions from an image, and if I want to classify them, then depending on my classifier output, I could try to explain things differently. So if I believe, or if the system is predicting that if it's a dog, then we could try to learn a different classifier, right? So because in that case, your labels will change, right? So in that case, maybe it won't be a red colored cross anymore. Maybe it could be a different colored cross, right? So depending on the way depending on the way that you are trying to explain the model working principle, so we have to look into the predicted label of an image, and depending on that, your classifier or your explanation parameters will change. Because if it's a dog, then that these pixels will be put, or the explainer will put more emphasis on these pixels. if it's a guitar, then the explainer will probably put more emphasis on these pixels. So the explanation space will be different, right? So the parameters that you learn after you run the explanation mechanism, the squared loss that I talked about, these will change. The 5 vectors will change depending on the predicted labels that come from theta. Okay. Okay. Now, from the per instance explanations, I think when we talk about explaining the whole model principle, then we need to aggregate somehow the individual instances or the individual feature weights from the instances. They should be aggregated somehow to get the overall model explanation. So the way we do is like, so in this example, you could see that there are 5 documents, and then these are the feature weights that you learn for each. So each row vector here corresponds to the output of, corresponds to the phi output that we learn from the classifier or for the explanation model. So these are the lines that we learn, right? So for each document, these are the feature weights that's coming from the square loss that we minimized. And if you want to explain the overall principle of the model, then we should try to select instances that kind of cover the whole feature space. In this case, if you see that if you take document D2 and if you take document D5, then it covers F2 and F3 as well as F4 and F5. It leaves out F1, which is, I think, desirable because you want to select a minimum number of instances, because if you select too many instances, then if you want to explain it to anybody with these many instances, he'll all get confused, right? So you'd want to minimize the number of instances for the explanation. So this is a bit like the set cover problem, right? So you need to given an entire set, you need to pick up an optimal subset that covers all the elements. But that's an NP-complete problem, and so it's not possible to solve it exactly or in an optimal way. So what people would typically do is they would apply greedy heuristics, which perform fairly well. I mean, for the set cover problem, you could show that that the approximation factor is like half, so it's guaranteed that it's kind of guaranteed that the optimal solution or the solution that you get would be like at most twice the size of the optimal. So that's not bad, but we can't spend lots of computational time to solve it in the true optimal way. But so, yeah, selecting features like this that covers the entire feature space, then you could say that, okay, so this look at D2 and look at D5 because that covers a different feature space. So that covers a different part of the working principle of the model. So maybe these are examples of documents that are on flu, and these are examples of documents that are on any other disease, which is quite distinct from flu. So that the model does well for both flu and for other types of diseases. Let's say, for example, cancer, right? So cancer is a very different disease from flu. So that your model works well on these 2 very distinct types of data instances. So that will help to kind of put more trust on your model, because it doesn't just do well for one particular type of instances, but it does well for many different types of instances, which are quite distinct. So in terms of the figure, so it might correspond to learning one classifier here and learning one classifier here, which is quite, just quite far from this particular instance, right? So that's how you need to kind of cover the entire feature space. Okay, so yeah, I think we have got, I've tried to cover the explanations in AI. Is there any question? Or else I would move on to the information retrieval side of things.
So Debasis, there was a question. Unfortunately, I lost my internet connectivity and just joined back. But there was a question around how a complex decision boundary was being approximated by a simpler model. So I think it is around the idea of Lime, I guess, that you're talking about here. Where,
yes. This is the Lime algorithm. Yes, this is the Lime algorithm. Yes.
Right. So I don't have the question in front of me, but I think it was around the fact that how can we create a simple model? I mean, obviously we've created a complex model to start off with because a simple model probably was not giving the accuracy. But I think maybe if you could just describe a little bit about how that local model is an approximation just in that locality, right? Where a linear approximation is being created.
Right. Okay, so yeah, as I talked about before, so imagine that theta is a complex model, right? So theta is already a model that you already have trained. So you know that you have trained theta on a set of X inputs, and then you had used the supervised learning. So you had used the true labels to train theta. And then let's say you have got a test set on which that if you throw in this particular test instance, so that's the predicted class that you get, right? So let's say, so these are all predicted labels here. So let's say you have this red cross here, right? And you throw in this and then you get the prediction, which is the red one. So the idea would be like you try to throw in similar instances to that particular red cross. Maybe you try to perturb some of the features, some of the data points, some of the data elements. So if that's an image, if X is an image, so you could try to so by sampling from neighborhood, we mean that you try to form other inputs. So either you have those inputs in your test set, which are very similar to this one, or you could also form pseudo inputs like the one that I'm describing here, right? So you could take, you could turn off some of the bits or some of the pixels from the images, and then you could have a pseudo image kind of thing, right? So, but given that local set, so in this case, so when you sample from this neighborhood, so you are giving it a local set, right? And then you are trying to learn a classifier based only on that local set. And how will you learn the classifier? You know the predicted outputs for all these points, right? So if that's a regression model, then you know that for each of the points you have a continuous real value. If it's the classifier, then you know that for each of these points, theta z will correspond to an integer. So let's say a binary classifier. So theta z, it's either 0 or 1, right? So in this case, you know that it's either red or blue. Now, if you treat them as true labels, then you don't learn parameters of theta anymore. You learn parameters of a simple linear classifier, phi. So you have z, and then you have a logistic regression that you train, the parameters of which will be phi. And the logistic regression parameters that you train for the current input x, that will serve as your explanation vector. So that's the concept.
Thanks, Debasis. One other question, I mean, with the image that you were showing of the dog playing the guitar, it seemed like it was more an acoustic guitar rather than an electric one, right? But the original model seems to be giving it more weight to the electric guitar.
Yes.
How does the explanation, are there mechanisms for feeding that back in to actually improve the original model itself?
Yes, I mean, that's something that you can do, but then in the first place that you should know that the model is behaving wrongly, right? So in this case, you know that the probability of getting an electric guitar is higher than acoustic guitar, which is wrong in this case, or the Labrador one. So probably I would have classified that to be Labrador, right, rather than the guitar one. But in this case, since you know that the probability is 0.32, the model actually tells you an explanation that why does it think that it's an electric guitar, right? So it's possible for a human to look into the explanation weights and then see that, okay, so if you just look into this part of the image, so if you don't have the part on the left, then might be you think that it's an electric guitar, right? Because you don't have this part on the left. So that's how at least you know that whatever the model is doing, it's kind of doing it in a consistent way, right? So whatever representation it's learning, so you say its prediction could be wrong, but you have an idea about why is it arriving at that wrong decision. So like know that if it's looking into the left part of the guitar, then you know that it's an acoustic guitar, and then that's also the model thinks. Like the model is saying, that tell me what to look at, right? So if I put more attention, or if I look more closely into this part of the image, then I believe that it's an acoustic guitar. If I look more closely into this part of the image, then I will think that it's a dog. So which perfectly correlates with the human choices that we make, right? So if shown this image and then if we are asked to pick one particular class, I think it'll be difficult for all of us. We won't be getting confused with the acoustic guitar and the electric guitar, that's for sure. But then for the dog one and for the guitar one, we'll have confusion, right? So we don't know which one we need to classify it to. So that's what the model is also doing. I mean, yeah, so it's saying that, okay, so if you want me classified as a dog, then I would look into this part of the image. And then from a human point of view, I think that makes sense because we can trust the model because it's doing things in the way we would expect it to do. Whereas, if you'd have, for the class dog, if it had pointed out in this part of the image, then we would know that, okay, so the model might have classified that into the proper class, but then the way it's arriving at its decision, it's something that's not correlating well with the human way of thinking.
Sure, but I mean, so we've taken a simple model to try and create an explanation for a complex model.
Right.
Now, it gives us insights and gives us some belief that, yes, it's not looking at the background of the image and saying this is a wolf, for example, right? I mean, that kind of thing. But it's a more complex problem to now feed that back into the complex model and say, hey, actually, first of all, you need to judge whether the local model was a good enough approximation to know whether the problem is with the explanation or whether it is actually a problem with the global model, which is complex and is not giving a good prediction, right? So is there some work that has been done around that to actually be able to somehow manage that complexity of, how to update the global model?
That's an interesting question. I don't think that people have that there exists work like that yet. I need to check literature. That's a very interesting thought. Okay. Yeah, I mean, that's interesting because I think what people typically do is like for all these explanation papers, they typically want to find correlation with human judgments. So they would show images like this to humans and then kind of ask them how much of trust you want to put to this model. If you see predictions like this, but then trying to figure out automatically, how good your explanations are. So I mean, yeah, I mean, you could see something like this local fidelity, could be an automated measure of how good your local explanations are, like how close it's fitting. Like we are training this local parameter, right? We are training this logistic simple classification parameters that we're learning. So how close does that fit to your inputs? Measuring RMSE could be a very naive way of seeing how close it fits, but I think that may not be sufficient, right? So yeah, I mean, I think what you are saying is perfectly valid, right? So we should be thinking about way of feeding this information back to the global classifier model, and then trying to see if we can improve the predictions. So if let's say if we have, or if we build these simple linear classifiers around a set of points, so we could imagine that we don't have a complex decision boundary anymore, but we have like a piecewise linear curves, right? In the extreme case. And then we could maybe we could select, or we could replace some part of the decision boundary with these piecewise curves, and that might help to improve the accuracy of the overall of the model. So I don't think that there is any work which is trying to do that. I'll have to check, but I don't know.
Okay, thank you.
Okay, so I guess we could move on to the next part. So this is about so this thing that I was talking about, moving from feature space to data-driven space for AI and for classification models in particular.
Debasis, sorry.
Yeah.
Sorry to disturb you. There's just an interesting question asked here. For n classes, do we need n different linear models, or like a multi-class problem? I mean, is it different for that compared to what it is in a binary?
No. For n classes, you would have softmax at the output. So if you look into this this equation, so theta z, it belongs to one particular class, right? So it could be k classes, so it could be k-dimensional softmax. So in that case, so rather than having 2 different colors, you can have 3 different colors or 4 different colors. So that won't be a problem.
Okay, thank you.
But
from a logistic perspective, if you're using logistic regression as the simple explanation, and that's kind of a binary classifier, so would you need to learn multiple linear regressions, right? Or I guess, are you suggesting we should learn
No, I mean,
a
yeah, I mean,
neural network with no hidden layer, then kind of the equivalent of N?
So this example here shows two classes, but then logistic regression, you can generalize that to multiple number of classes, right?
Right.
So that won't be a problem. So we could, I don't know. So if you have got three different classes, so if you train logistic regression, then you'll have two different lines corresponding. You could train them pairwise as well. But the way it should work is like it should directly. So maybe it's difficult to plot that as one single line. You'll have two lines definitely,
right?
Or maybe a curve. So it's shown here as a line because there are two classes. But then from the objective function point of view, it could be this could be a discrete number, right? So it doesn't need to be 0 or 1. It could be a discrete label. So the only thing that you need to consider is like you need to choose one level, right? So if you are coming up, so if there's a softmax of the output, you need to choose one particular class. Like for instance here, if we choose dog, then we get a different set of parameters. If we have chosen some other class, then we will get a different classifier parameters. So you need to make these choices here. So for theta z, you need to make that particular choice, that which class does that belong to.
Right. Perfect. Thank you.
Okay, so yeah, I guess we could move on to the information retrieval part. So yeah, as I was talking about, so this paradigm shift from feature-driven to data-driven models is something that's already people are trying to apply this for information retrieval as well. So in information retrieval, so what we do is, we are given a query and we need to retrieve a set of relevant documents, at preferably at top ranks or the first result page of a search engine. And so typically, what we do is we estimate some kind of similarity function between a query and the sets of documents that are there in my collection. And then based on the similarity values that we compute, we try to sort them in decreasing order, and then show these documents as a ranked list of documents that we retrieve. The principle of deep learning. So in statistical information retrieval approaches, we know what are the similarity functions that we want to compute. So let's say it could be variations of TF-IDF. So we know that how many times does a term occur in a document. The more number of times it occurs, maybe it's more important or it expresses the topic of the document more closely than the other ones. So this will not be true always, because there could be a list of function words, like the articles and the prepositions. Don't really need to consider them because they are not adding to the topic of the document. So we generally take something like an IDF. It's called the inverse document frequency. So the similarity score that you compute for a document and the query, it involves selecting terms with high TF-IDF values. And it could be variants of TF-IDF as well. But that is true for statistical information retrieval approaches. But for deep learning ones, what we typically do is, we'd want to separate out a relevant document from a non-relevant one. So assume that we are given a training set of relevant documents and queries. We'd want to use pairwise training and say that, okay, so if D1 and D2 are two documents that is given to me, I predict a binary response of 1 if D1 is relevant and D2 is not, and 0 otherwise. So in that case, you'd want to generalize it to other queries. So this is how deep learning, or this is how learning to rank works for the pairwise case. And in the pointwise prediction, so in the test case, you typically apply the same model, which you have trained in a pairwise manner, and then in the testing time, you simply predict a score. But given a query, what is the likely score of this document? So typically, there are so learning to rank approaches, they have also seen an evolution, because earlier days, people used to have features like, features from a query log, like what is the position of a document that was clicked, and some other features like what was the TF-ID of weight for this term in that document. So features used to be hard coded initially. But nowadays, features are, you don't explicitly engineer features anymore. So what we typically do is nowadays is, given a query and a document, we typically compute the pairwise matrix of word to vec or word embedding similarities between terms in queries and those in documents. So let's say your query is, I don't know, bone disease, and document, there is some document about osteoporosis. So you know that osteoporosis and bone disease, they're very similar concepts. So in the query, if you've got bone and disease, you take pairwise similarities of osteoporosis with bone and osteoporosis with disease, and then so on. And then you typically form a histogram of the similarity values. And then you'd have to quantize them. So this is a deep relevance matching model. It's called DRMM on the left. So it computes these pairwise similarity values of word embedding similarities, and then it plots them. It quantizes those values in discrete ranges. So let's say this is the interval from -1 to +1, and let's say there is a spike here. So it says that values from 0.3 to 0.4 are more frequent for this document. So word pairs that have similarity values between 0.3 and 0.4, they occur maybe 10 times for this particular document. So it gives you a pattern, in the histogram matches of the word pair similarity values. So then that's how you form the histogram in the first phase. And then you feed the histogram directly to a feed-forward network to predict the score. So either you can train that in a pairwise manner, as I said, or in the testing time, you use that in a pointwise manner. But the idea is like, you have to transform a query and a document, into a histogram of word vector similarity matches, and then you feed in that histogram, to discover some patterns, that you could typically use to separate out relevant documents from the non-relevant ones. But this is very different from what we would typically do. Like, so we would typically look at, when we look at a document, we typically see, how many times does this term occur, and what is the, how frequent is that term in the collection, or how important is that term in this document, right? So for these models are very, very far from that way of explaining relevance to IR practitioners. And maybe to search engine users, if you are wondering about like, why is this document retrieved at that particular rank, so it's very difficult to explain why is the model retrieving this particular document at this rank. So yeah, let me talk about how explanations work for IR. So yeah, as I said, some models may not be easy to explain to a search engine user because who could have questions like why is this document retrieved at this position? So eventually you would want to capture the local effects of subsamples and predict distribution of terms. So just like we have done for the line case, for the classification algorithm of explanations. In this case, you could try to see a clear analogy that given a query and a document, from the document side of things, you need to subsample and you need to form pseudo documents and then see, how is the IR model behaving for that subsample of document. So the subsample is guaranteed to be quite similar, because if you're leaving out 5 terms from a document of 100 terms, the cosine similarity of that pseudo document is also going to be quite high compared to the original document, because we're just leaving 5 terms out. But by leaving terms out, so if you leave out important terms, then probably that you're going to decrease the rank of that document quite a lot. Whereas if you are not leaving out important terms, then probably you're not going to change the relative rank of the document, right? So change in the relative rank of that document or change in the relative score of the document will give you an idea about the importance of terms. So that's the idea that we want to use here, or we used in this paper of ours, so which was published in Sigaya 2019. So the whole idea is like taking subsamples and then trying to estimate importance of terms. So the idea is expressed like this. So it's very similar to Lime. If you look at this equation, so phi is the kernel function here that So I talked about that. You form the subsamples of documents by leaving terms out. So this is the kernel function. So it measures how similar is this subsample to the original document D. So the closer this subsample is, you put more weight on that. SDQ is the total similarity of the whole document with respect to the query, and S parameterized by theta. So this is the this importance weights that you are trying to learn. So this theta is equivalent to the phi in the earlier equation. So that's the subsample that you have formed, and then you are trying to measure the score of that subsample with respect to Q, and then you are trying to fit a linear regression on these score values, and then you have a regression parameter here. So if you train this objective function, the parameters are theta, so you basically get a representation of that document, right? So of the whole document, you have this parameter space comprised of, let's say, 100 terms. If you have got 100 terms in the document, so this theta vector, will be a 100-dimensional vector, which will give you the term importances, right? Yeah, so I talked about that. This is the kernel function, and yeah, so theta is the parameter vector used to approximate the score of the subsample di with respect to the query Q. We can skip over this. Yeah, so the whole idea is like, so after you estimate theta, so as I said that, if you had left out important terms, then probably that will lead to a lot more decrease in the scores of the documents. And then by that, you could compute the scores, of the important scores of the terms. And then typically what you'd expect is like, if you look at the theta value, then you would expect the terms that were really important for giving that document a high score, would possibly get a higher weight here. And that's something that we can verify in the next example of ours. But yeah, before that, let me talk about. So I was talking about different ways of forming the pseudo documents or the subsamples of documents. Now you could try to use different sampling techniques. So you can use uniform sampling. So you could select terms at random, and then leave out terms at random, and then form the pseudo documents. Or you could have some bias sampling, like you could already know that the terms that have got higher TF-IDF weights are expected to be more important. So you could give more emphasis on them, and you could try to sample them, or you could try to retain them, and then leave out the ones that have got lower TF-IDF weights. So you can do that. Or you could do something like a mask sampling, because how we humans perceive reading a document is like we won't be sampling terms at random throughout the document, but we'll be looking at windows of terms. So so you could have something like a masked sampling, where you could say that, okay, so I select a window, and then I decide to mask this window out or not. So this could be chunks. This could be based on chunks as well, right? So you could say that, okay, so what is the probability of selecting a chunk, and then what is the probability of making this chunk visible, or making this chunk go to my sample, to my subsample, right? So in this way, you could leave out chunks from the document, and that would involve, or that will ensure some continuity, in the document text that you are seeing. So we experimented with all of this. So here are the results. I mean, yeah, so this is an example for a query. The query was counterfeiting money, and these are examples showing the different weights from the different sampling techniques that I talked about. So each sampling technique, if we employ the sampling techniques, we'll get different explanation vectors. So the explanation vectors are like, so if you look into the explanation vectors, you typically see a high weights for the query terms. Like for counterfeit and money, they are both query terms, and for both of them you get high weights, right? So that's a good thing. And for the mask samples, you could see that there are other terms like agent and Phoenix, for which we get lower weights. So probably these terms were not that important, right? So maybe it's talking about very specific cases of counterfeiting money, but maybe that's not something that we want to look at, right? So we want to look into a general, we want to find out documents that are generally relevant about counterfeiting money, and not very specific cases, which happened 25 years back. So in that case, so it makes sense to have low weights for these terms here, like Phoenix and agent, and something like scheme and something like trade. They have got higher weights here. So if you see that a document is relevant, you'd want to know why is that brought at top ranks. So in this case, if the explainer algorithm shows you that it has put more emphasis on words like trade and scheme, and that's the reason why it had brought this at a better rank or a top rank, then that kind of provides you an explanation, and then it provides you more trust. It helps you trust the model more than some other model. Okay, so I will stop for any questions at this point before I move on to the next part.
So in the case of information retrieval, Debasis, we would expect that documents that are highly ranked are containing words that are considered to be semantically related to the query terms now, right? We've gone away from vocabulary-based matching.
Right.
Just based on inverted indexes, we are now looking at that embedding, right? So, I mean, isn't that enough of an explanation that, why do we need to randomly perturb the values here, where we could just pick up what are the words that are just semantically very related to the query terms, right? I'm missing something here that I haven't quite been able to catch yet.
Yes, I mean, yes and no, but so the thing is like, if you look into the working principle of a ranking model, so it may be the case that, like I was giving this example, where is that example, like this one. So it's not just looking into the total semantic similarity across documents and queries, because there are other aspects to it, like the document length and factors like how important are the terms from the collection perspective. So things like this could be more important, right? And the question here is like, so semantic similarity is one feature that you might think, but then there are three more features, like the term frequency of a document, how frequent is that term, the collection frequency, which gives you an estimate about the importance of that term, and document lengths as well. So, so the explanation here is trying to figure out how does the semantic similarity, is interplaying with the three other basic similarity features that we know it's very useful for IR, and then trying to understand that, okay, so if it may be the case that if you're retrieving a document at very top rank, maybe it hasn't got those words, in high frequencies. Maybe the query words they are not that frequent in that document, but we somehow need to explain that, okay, so why is that the case? Because it has got terms that are similar to the query terms. And because this query term is more important than the other one, because counterfeiting money, because counterfeit is a more important term than money.
Right.
Money has got a general semantics to it as well. But counterfeiting money as a whole, if you could find out terms that relate to that concept, because concept of counterfeiting money is quite different from money, right? So
right.
Trying to figure out, something like that. Yes.
Right. Makes sense. So you're actually even taking into account trying to, identify in the query terms itself that there are certain terms that are more important compared to the others, and that's implicitly within the ideal gold standard ranking of documents that you're given.
Right.
Okay. There is a follow-up question actually on the first part of your talk. Sai Nikhilesh is asking, the example that you had given, it was not necessarily just a multi-class, but a multi-tag problem, right? With an image that may have multiple tags associated with it. So for example, if you're extracting objects from an image, here to say that, yes, Labrador is relevant, but so is guitar. Right. So you have multiple labels.
Yes.
Are you saying that we need to, for every one of these tags now, create a separate linear model, or are we treating this as a multi-class?
No, that's what we should do, right? So if you want to extract, bits and pieces. So in this case, we are extracting regions from the image, right? So you can imagine that this is more of a region extraction problem for the image. Or for
Right.
text, you could have an information extraction problem, right?
Right.
So let's say, from a large document, you want to extract bits and pieces, and then let's say, you want to extract names of people and names of locations. So they are different classes, right?
Yeah.
I think in that case it makes sense, because so coming to the image problem, yeah. So if these are different concepts that you were extracting from one single image, then you should want to look into the predictions for each, right? So if
Right.
this so if it's saying that there is a dog, you'd want to know the why does it believe that there is a dog in that image, right? So
Right.
that's why you explain, or you learn the classifier, the local classifier, and then look into these parts of the image and then believe, okay, so this prediction is correct.
Perfect.
Whereas if you look into the electric guitar example, so maybe that this is not correct, right? So it should have looked into a bigger perspective. So it should have looked
Right.
into the left side of the image along with that longer part, and then made a decision that it's an acoustic guitar, and
Right.
not an electric guitar.
Perfect. Okay.
So
Thank you.
things like this make sense, even for text. If you're extracting many different things, let's say you have got long passage, and then you're asking multiple questions, and then system is answering questions, all these different questions. Then you have to do that for every different question that you are asking, right? Because in a whole document, you could have answers to multiple questions,
Yeah.
and it makes
Perfect.
sense to do this local classification for all of them.
Yeah. Okay. Great. Thank you. Thanks. Sai, hopefully that answers your question.
Okay, so if there are no more questions, I'll just try to go to the concluding part of my talk. Where I will talk about. Okay, sorry. Yeah. So basically, I'd want to conclude my talk saying that this is something that could be highly useful for active learning, because in active learning, what we do is so we have lots and lots of unlabeled data instances. And we have a very small subset of labeled instances. Like, so in this case, we know that we have a very small number of points that are colored as red, and a very small that are colored as green. And then we want to learn a classifier which will distinguish between the reds from the greens. So we could start with a small subset, but then given that we have annotation resources, we could try to plug in annotations for more data points. So we need to annotate them, but then from the algorithmic side of things, we need to be selecting the subset of data that we'd want to give to the annotators for the labeling process. We don't want to give them something that's very similar to the ones that they already have annotated, right? And we would want to give points to them for annotation, for which the classifier that we have trained, with that small subset of labeled data sets, that classifier is not feeling that confident about those points. So in this case, the decision boundary that we have learned, it's a blue line like this. And there are points that are quite close, these black points over here that are quite close to this decision boundary. So if it's very close to the line, to the boundary, then these are the points about which the classifier is the least confident about. So in that case, maybe it makes sense to assign these points or to include these points for the labeling process, because once we annotate these points, so if we know that this point over here is a green, so maybe that will change my decision boundary in a favorable way, rather than knowing that what this point is, because probably we know that that's the green, right? So these are very far apart from the red ones, so we probably know that that's the green. So there's no point of putting that point or throwing that point for the annotation process. So this is how the active learning principle typically works. So it employs something called uncertainty sampling. So given the set of unannotated points, it tries to classify them based on the small subset that we already have. It computes the uncertainties in the posteriors, and depending on how uncertain they are, they try to rank the points and then include them for annotation in the next phase. So what I want to say here is that rather than simply looking at the uncertainty objective, so we know that. So what is the motivation? The motivation is that, like, if we include more points, then we get to a point where we can improve the effectiveness of the classifier. But that's the only objective in active learning, which people have used nowadays or till now. But what I'm saying is that we could also look into other objectives like how explainable will the classifier be, like how understandable or how interpretable will the classifier be. So rather than trying to include points only on the basis of the uncertainties in the posteriors in order to make the classifier more effective, maybe we could sacrifice accuracy a bit and then go for models that are more explainable, from a global point of view. So this is one of the objectives that could be incorporated within the active learning scenario. Now you want me going into the details. So the algorithm is like, so we have to do this in batch, right? So it's a bootstrapping process. You start with a small subset of instances that you already have annotated. And then, as I said, that you need to classify the rest of your points. And depending on how uncertain they are, you include them. But then in this case, you could employ another different objective. So it could be a combination of both uncertainty and the diversity of the explanations. So, and as I said, so given every point, you could transform that to the explanation space. So which means that, given every point, you learn these local, interactions with the rest of the points, and then you have a simple linear fit for that line. And so you could imagine that that line is a representation of that point in the explanation space. And if you do that for all the points, for all the black points in this figure, so you get to know that what is the explanation, or what is the explanation vector representation of those points, right? And then depending on these representations in the explanation space, you could try to select points that offer more diversity. So which means that, so the thing is, like, if you have seen an instance, which is which uses, many different feature vectors for explanation. So coming back to the example, right? So let's come back to the example here. So in this example, let's say you have seen, so in the active learning phase, let's imagine that you have seen this one and you have seen this one. So this exists in your seed set, but this is something that this is not annotated, and you see that these are the explanation weights for this point. But you know that there is kind of overlap, right? So with the seed set and with this one, maybe this part of the guitar, it overlaps. So you know that probably, although it might help you to classify or to distinguish between electric guitars and acoustic guitars, maybe you don't want to include this for annotation. Maybe you want to include this image or this part of the image for annotation, right? I mean, the example is a bit, it's not going to work for this because you're going to throw in instances, right? But the idea is like this, right? So, so in this explanation space, so it uses a very different explanation space, right? So it uses a different part of the image or different feature vectors, to explain, the class of this particular image. So maybe it's a better idea to throw in this instance for annotation than this one. So that's the overall objective in the active learning that we are talking about. So this is what we do. So we find out how diverse they are in terms of the expansion space, and then we try to include the most diverse ones in order to get to models that will be more explainable. Yeah, and then so we have some results for the MNIST dataset and for the fashion MNIST dataset. So this is the results that we obtain with the uncertainty sampling, and these are the results that we obtain with the diversity factor, with the expansions included in the active learning phase. So it turns out that if you want to see why is this image classified to a 0, then if you just include the uncertainty sampling as we talked about in the active learning, the standard active learning scenario, you get to a model. Eventually, you get to a model, which looks into, okay, so this part of the image, but not very closely, right? So you don't get too many red points here. But if we include the diversity factor, with the explanation vectors, then we eventually are building a model with the same amount of data, but with different instances being annotated, but which helps you kind of, or helps the model to make its decision based on, these points with more confidence, because it's a zero, because if you have this part as well, and not just this right part, you should have a circle like this. So this is how you could get to models. If you start with a very small data set, you could get to models which could be more interpretable and more explainable than if you had just considered uncertainty sampling. You may have models that could do well, but then it's difficult to explain why it's doing well. And I think with that, I'll conclude my talk with just one particular application for the societal benefits of this. Because as I talked about the scenario that AI, it needs to be fair and ethical, because we are going to rely more and more on AI in our coming years. And so if we are not able to build models which we are quite comfortable with and we understand how it works, it will be difficult to control these models. Like it could end up making unfair predictions. Like, say for example, for the IR case, if you have a query like CEOs, and if the document, or if the search engine retrieves a list of documents like this, a list of images like this, so you see that there are only 2 women CEOs that it has retrieved, whereas in the US, the actual ratio of women CEOs to men is 27%. Whereas in this image, out of 10 images, there are only 2, which means about 11% of them is actually represented in this particular small top 10 results. So top 10 list is not actually achieving the true recall rate compared to, if your query has got some demographics associated to it, then it's not catering to all, or it's not properly representing that demographic group in the top 10 results. So this you can say it's not that fair from that demographic group's point of view. And similar things could happen for different races of people, and for different other, if you define other ways of classifying attributes to entities, it may not achieve the true recall rate with compared to those attributes. And something like this is also evident in query autocompletion, where you type in Scarlett Johansson, and then you don't get any suggestions about the filmography of the actor. Whereas if you type in Brad Pitt, then probably you will see films and many other filmography related stuff to Brad Pitt. But this is clearly not fair. That results should be different. So for both of them are actors, but then results should be different because Scarlett Johansson is a female as compared to Brad Pitt. So things like this. I mean, if we want to address these issues, then we need to be building models that we better understand. And as I said, this could be possible with active learning, right? So with active learning, by incorporating the objective for the expansions, when we build the models gradually from scratch, then at every point of time we can kind of ensure that we are trying to build models that we can better understand, and that will give us more flexibility of tuning these models and to have better control. So I'd want to conclude my talk and then take in questions if there are any. And thanks a lot for inviting me, and it's pleasure. The pleasure is mine to deliver this talk. Thank you.
Well, thank you, Debasis. Your talk has lived up to expectations and beyond, right? I think the examples that you gave at the end are very interesting examples. In a world where knowing what is true is becoming more and more difficult, how do we figure out as to, the statistics that you're talking about, right? So, for example, the fact that 37% of CEOs in the US are women, and trying to take that as a gold standard to then impact our retrieval. In a world where it's so difficult to know what is true and what is false because we're being hit by so much fake information, how are we going to balance that in your view?
Well, that's an interesting question. I think from the research point of view, I think if you want to address the fairness side of things, so I think at the very minimum, you need to have some additional information with your data, right? So if you just have the data, then it's very difficult to see, if you are retrieving or even if you're classifying it's very difficult to see what you're classifying against. That could go against some of the groups, right? Like let's say, if you are given images, and if you're predicting that how likely it is from the face of the person, how likely it is for the person to be a criminal. And you could have data of criminals, and it's very easy to generalize it to the case that if you see the skin color is black,
Yeah. Yeah.
then you predict that it's more likely for that person to commit a crime. But that's something that a human won't do, right? So probably he won't overgeneralize. But it's very very easy for AI systems to kind of see these patterns within the data, and then try to learn these generalizations. But these are not good things, right? So
Yeah.
if you are building explainable models, and then probably if there is a way, I don't know how, but if there is a way to see that, okay, so this prediction of the system is because of the skin color of the person. So it's not possible to see with the overlapping of the image, because with the overlapping of the image, you could see distinct images or distinct parts of the image. But to visualize something like skin color, maybe we need different other explanation, techniques of visualizing. How does it take that into account? But if we had that, if we have the metadata, firstly, that we should know that it corresponds to a black person and a non-black person. Even if we don't have that, moving ahead in the future, because it's very difficult to annotate all this metadata for all the data instances, right? So even if we don't have that, if we build explainable models, and if we see that what the model is abstracting out, a part of that corresponds to the skin color of the people in the images. Maybe it shows clusters and says that, okay, so this is a cluster which has got white colored people, and this is with brown, and this is with black. So if it can segregate out the inputs on, and if it can base its decisions based on not based on the skin color. So these things could be very helpful to. So this is applicable for classification as well as for ranking, for any other AI based predictions. So you need to have attributes to the data. Even if you don't have the attributes, then the explanation model, or the AI model should be kind of inferring or abstracting out those attributes from the data.
Thank you. There are a couple of questions here very quickly.
Yep.
One question is around, again, back to that Labrador image and the fact that the hands were actually human there, right? And we haven't focused on that. Is that only because the labels that we are looking at here are not picking up that, right? So that's the reason why we're not trying to explain that piece. Is that correct?
Yeah.
Okay.
I mean, it's
Another
difficult for a
question.
human to see that the hand is got of that of a human, right?
Right. How do we model bias so that we are able to test if it is biased or not biased, right? I guess this comes back to, again, what you were referring to, the skin color. And
Yeah. I mean, that's an interesting question, right? So I think from the system's point of view, I think it should be guided somehow to say that, okay, so maybe this has got more reasons to be biased, because you could have non-uniform posteriors. If you think about the predictions, and if you think about the attributes, you could have non-uniform posteriors. So you could say that my system is predicting that men are more likely to be afraid, but probably you are going to take that humorously, right? You are not going to be very serious about it. But if you're saying that women are more likely to be afraid, then probably that will involve an element of long-term injustice that has happened to women for the past 50 years or so. So there are some associations of the attributes with the classes that could lead to injustice, or it could be testifying for testifying the injustice that has happened to that demographic group for a number of years, like predicting that black people are more prone to be criminals, and then women are more prone to be afraid, or they are more likely to be homemakers. So these could be like objectionable statements that the system could be making. Whereas some of them, for the men, or for even if you say that white people are more prone to be criminals, probably it don't matter that much, right? So
yeah.
there has to be some element of human, I think, control on defining, what associations could be treated as injustice. There has to be some human element to it. Yeah.
Yeah, and I think that this is more a comment rather than a question, but referring to the fact that it was very interesting that you talked about how you're trying to bring in active learning, but not just taking into account accuracy of the model, but also explainability. And the idea is kind of very kind of interesting. If the explanation of two very close points varies greatly, then what should we do? Is there a simple answer to that even?
I think then it makes sense to kind of relook at your data set and then relook at the annotation process, right? So if you need to look at those data samples and then kind of see that, okay, maybe there was some mistake in the annotation or something. So it's a good thing that the explainer is able to catch these things. So that could also be, helpful to have a relook at your data set and then trying to rectify some of the mistakes that could have happened.
Right, and even the definition of similarity, I guess, needs to be looked at, right? I mean, it might actually be similar based on certain dimensions that are not interesting. So, yeah.
Exactly. Yeah.
Can we gain confidence in the reliability of our AI system without an explanation of how it reaches conclusions? I guess the answer to that you have given already, which is no, right? So,
yeah, I mean, people had other ways, before the explanations came in. And people used to look at the posterior distributions, right? And you just looked at the probability, like if it's high for one class and low for the other classes, then you believe that, okay, so your prediction is confident, or you have confidence in your prediction, right? So coming to the example of the active learning case, where we had the black points. So you'd want typically the black points, not to be very close to the decision boundary. So if it's very close to the boundary, then you are not sure, to which class does that belong to.
Right.
So that was the only way of finding out confidences in classifiers. But with the explanation mechanism, you are transforming that to different space. You are able to use more information in kind of reducing the confidence about classification.
Right. Okay, great. Thank you, Debasis. This has been a wonderful talk. Thank you so much. It's really been very enjoyable to listen to your research work, and congratulations on the great work that you're doing. And we hope that we will be able to entice you to talk to us in the future as well and give us more insights into the cutting edge of information retrieval and deep learning in general.
Thank you. Thanks a lot.
Thank you. Thanks so much.
See you then.
So folks, the next session is on supervised learning. I'm just going to, Madhukar is here. I was just going to look for you in the partisans. Madhukar, thank you for taking the time out and coming